So in the last lecture, we have reviewed the basic syntax and how can you formalize a theorem. So in this lecture, we're going to help us to we're going to together to formalize and prove some of the theorem statements. So the first lecture, at the end of first lecture, we introduce a mechanism to prove the theorem by calculation. So here's a two link if you want to get access to the notes. The whole notes is in these two links. And second one is the online platform for this course. So if you join the online platform, you can join us to together prove something and write your own theorem. You can take a picture and get access to the note. This note contains all the theorem answers. So yeah, that's all. And in the last lecture, we have introduced the tactic proof, which is the mechanism to allow everybody to prove a theorem step by step. You can get access to proof from a few small fractions and use this tactic mode to connect all the things you have proved together. This is some of the tactics I introduced last week. And the first simple tactic is that rewrite, apply, raffle, and cork. We haven't introduced cork, but we have introduced the previous tactics. And the second one is the medium tactics, which includes some of the automatic rules, and it's a rule-based simplification using these tactics. This tactics also depends on the specific structure of the type you're in. So if you want to use these tactics, you have to make sure your type is in the correct structure. For example, if you want to use the ring, you have to have a structure of ring. The type have to be a ring. Yeah, I will later explain how this work. So since we are going to do the formalize, and in the first few lectures, we're going to do our proofs in real numbers. So I'm going to explain a few details about real numbers. So the first thing is this word is called axiomatization. So what is axiomatization? It's a term in the logic world, which means when you want to formalize a theorem, a theorem is composed of all the variables and logic connectors, and the collection of all these variables and logic connectors is called a theory. A theory maybe contains many propositions, many theorems, many lemmas, and finally maybe you want to prove something. This whole set is called a theory. So how can you formalize a theory? In mathematics, we first specify a small set of propositions or variables. We call it axioms. We assume it to be always true. And on top of these primitive axioms, we build all our lemmas and theorems. And however, in Lin, it is very crucial about how you choose this set of primitive axioms. If you choose all the axioms from different set of axioms, you can derive all the theorems and lemmas, all the facts about this theory. But if you choose a very old or very different axioms, it may be very hard. You maybe spend a long time to formalize some of theorem, and it may be hard for you to continue at some stage of formalization. So this is called axiomatization. So when we want to prove something in a type, we first need to get some information of how Lin used to formalize this, to axiomatize this theory. So the axiomatization of real number is always hard in mathematics, in the history of mathematics. If you have learned calculus or analysis, right? It's all about some Dedekind cuts or some completion theory, right? But in Lin, it chooses a quite simple way, which is to use the rational number to construct everything. So rational number is somewhat a simple thing, which means it's just a tuple, and the first is nominator, the second is denominator, and you have some rules. For example, you do not want your denominators to be 0, and you want your nominators and denominators to be co-prime so that you get a unique rational number instead of many tuples of the same value. So when you define such rational numbers in Ling, and based on these rules, and the computation of rational numbers is quite simple. We can see from later code, and because it's just the computation of these tuples, and for the real numbers, it's just the equivalence class of Cauchy sequence in rational numbers. I won't explain this into details. The basics that all the sequences, all the convergent sequences in rational number composed of the real numbers. So what's the advantage of this kind of axiomatization? It's the advantage is that you can transfer all the properties you have proved in the rational number directly into the real number, because it's just a convergence of sequence, and each item of sequence is still a rational number. We'll see how Lin used to formalize in this way. So in the when it's formalized the theorem in this way, it can get access to all the properties of real number. For example, on top of this definition, we can define we can derive that real number is a group, and it is also the commutative group in respect to the addition, and it is also a commutative ring, which means the multiplication is commutative, and another important thing is that it is also a group with zero. This is a bit hard to understand, but the basics that you have a group, and you, in addition to this group, because group only have the identity, right? In addition to the group, you also have a zero. So many systems have this kind of behavior. For example, like rational numbers, real numbers, maybe other things in algebra. So a difficulty in Lin is that you have these structures, but how can you define the division in this system? Because when you divide zero, you will always have some undefined number, right? In normal mathematics. So in Python, if you do divide by zero, it will give you an error that you cannot do the division by zero, right? But in Lin, it's a formalized language. We do not expect it to just halt in the middle of the program, right? So we give an additional definition to this divide zero, which means we still define it to be zero. How we can do this? How we realize is that we define the inverse of zero to be zero itself, and and we define the divide to be the multiplication and inverse. So this is how we formalize this division thing. So after the formalize of this division thing, we get a group with zero structure, and on top of this, we also have a field. To notice that to add this axiom, which is A divide zero, won't change the essence of this structure, which means all the properties you expect will still be true. Just apart from that, we have divide zero equals to zero. When you do the proof, you will see this fact. So what I marked in the right-hand side is that in each structure, the tactics you can use, because the real number field is a very large field. It contains all the ideal properties we want in most cases. So all these tactics will be true. For example, a group, a bell means the simplification in commutative group, and group means simplification in group, and so on with ring and field simp. Among all these tactics, the field simp is the hardest because it has the most delicate design of simp lemmas. It uses very specialized simp cycles to do the simplification. So we'll see from the code how this works. I won't use the online platform here because you cannot do the jump and back. So Last time we have reviewed, we have do the rewrite calculation, right? We use rewrite tactic to simplify some kind of equality, and which is just in a sense a regex max to match the item we want and replace with the new one. This is how rewrite work. So from this we continue. And first thing we can check the real number, how we define real number in the link code. I will make it larger. Wait a minute. For the real number here. Wait a minute. And we want to jump to a definition in ling. We press Control and then press this item, so we can jump to the actual definition in ling. If we want to check its original definition in Mathlib, if you have installed your ling on your laptop, you can try this operation. So you press Control and just jump to the actual definition. So here we can see the definition of real. Real is the completion of Cauchy sequence. The completion of the Cauchy sequence is very simple. We can see from here. For example, pi is a rational number which lies in the real number field, and this sequence is a typical example of a Cauchy sequence because it will converge to pi, which is an irrational number, but each item is a rational number. So this is how we define real number out of the rational number. So this is how ling accomplishes this, and we can also check how it defines the rational number. So from this structure, we can see that this proposition contains all the things we need. First is the nominator, and the second is denominator. And we also need a proposition say that denominator does not equal to 0. And at last, we need the denominator and denominator to be core prime. So these four propositions or a two variable plus two propositions constitute the definition of rational number. So out of this, we can derive all the properties of rational number. That's where everything gets started. So maybe you're also curious about how ling realize the integers and natural number. This is a bit of our course, but a natural number is based on the Peano axioms, and the integers is defined on the natural number. So actually in ling, everything can be reduced to the level of natural number. So if you have natural number, you have everything. We just, of course, with the logic structure. So this is how everything started. So maybe in Python, when we refer to the real number, we just do the calculation. But in ling, the realization of the calculation is decided by all this different stuff, all this axiomatic stuff, to build a tower of formalization. Yeah. And maybe we can also see how many structures on the real number it has. In the next time, I will explain how this work. Because when we press into this, we'll see a keyword called instance, which identify the structure of a type. When we want to define a structure or identify a structure on a type, we use instance keyword. I will explain later when we try to design a whole series from scratch. We want to dive into this now. This example is just to illustrate that how can we know the structures on real number. If you have other objects, for example, a group ring or some other stuff, you can also use this things keyword to check whether this type has the expected structure. So we can see this is what we have talked about. the commutative ring, the field, group with 0, and in addition is a linear order field. This is not give by granted. This is also something to prove because this actually defines an order on real number, which means you can do the larger, smaller, do the comparison between different number. If you do not have these instances, you can do larger or larger equal than something like this. So all this stuff together give rise to the word we're familiar now in the mathematics world. So now we're going to explain some more stuff. Let's see, which is a first complex tactic in the computation world. In the world. Okay, sorry. Wait a minute. Which is calculation, which is a cock block. So cock block allows you to prove the equality in a very natural way, in a very very neat way to write the sequence of equality. So you can see from the left hand side is the proof I write by hand, and the left hand side is the cock block. The cock block work step by step, which means you want to prove in this theorem we want to prove the square root of a plus b, and you want to do it step by step. Maybe first you expand all the bracket. The second you change some of the second step you change some of the order of the item, and in the last step you combine some of the order, and finally you get the proof you want. So of course, in our computation proof, we just do the compute. We just calculate, right? But in Lean, each step you compute, you have to provide a reason of why this equality holds. For example, in the first step, in the first step of this equality, we prove we just expand all the brackets. So you need to explain how we expand this bracket. This is by some of the rules. So you can do this calculation. And in the second step, in the third step, each step you compute something, you provide a proof, and all this compute sequence, all the calculation sequence plus the reason you gave will constitute a whole proof of this equality. The first one, the first item of the proof is the left hand side, and you will end with a right hand side, which is things you want to prove, and you connect all this equality, you get the proof you want. So I will show you how I do this. Okay, so at this time step I can show you how to prove this thing. So sorry, it wasn't responding. I do refresh. If it's not responding, I will turn to VS Code. Okay, let's wait for it responding. So I will show you how to prove this. So we want to prove this equality. The first step, we write down the first step we want to prove. The first step is that we want to prove this first equality, and we of course we concatenate by a by to enter tactic mode, and we will write different thing to do this. The things we want to prove will pop up on the info view. So this time we need to fill in our own tactics. For example, we have a multiplication. So I think the things we need to do is small add, and since now we have expanded the second item, and now another lemma we need to use is add more. Add more means to expand the first item in this equality. And we can use add more. Let's see if we get the goal. We still use another times of net add more because there's a two item of bracket here. We use another time. And here we close the first goal. And now we have proved this equality. We have proved something, but this is not what we want. On top of this, to continue our proof, we start from here. And in the next line, we don't need to write this again. We use a underline to denote this is our next step. So next equality we want to prove is we change the bracket. We change the bracket in this proof. So we also start by to interactive mode, and we use the associative property of the addition. Yeah. So we can still do the rewrite. The first thing we have is we want is to identify this large bracket, and we want to add a bracket here, right? So we first do an inverse order of add bracket, add associate. So if you tap a left arrow, which means you rewrite in an inverse sequence, this notation means that you just change the order of the right hand and left hand side of the equality and do the rewrite again. So after this, you will notice that the first bracket has been eliminated. So in the second step, because there's so many addition here, we want the link to make sure it rewrites the correct thing, right? So if we directly use add association, it will not work because it's just rewrites a different item. This is not what we want. So we can see that from this theorem, there's a hole. When we hover on the theorem, we can see the actual type of this theorem. Right. When we hover on this theorem, it will pop up a window to show what this theorem is about. So we have 3 holes to fill in actually, which is A, B, and C. So what we do to make link know which item we want to rewrite? We can see from our theorem that which is A is, of course, we want to add bracket here. So what the operation we want to do on is these three things. So we want the link to know that A stands for the A multiply A. So we type it here. Let's try. What's the problem? And the bracket. Yeah, when we explicitly type A here, it will get the correct thing to write. It will know the add association is on this thing instead of the whole addition. So this is a bit of advanced technique of rewrite. Yeah.
How do we know, like, do we need to put what B or C?
We don't need to fill in B or C. So in traditional interactive prover, we need to provide everything, every param of the theorem to get the system know what to rewrite. But in Lin, because it's a dependent type, it can automatically deduce what B, C is. If it failed to deduce, if it failed to compute what BC is, it will give you an error that it failed. So actually, you can see from here that Lin is a very computational intensive interactive prover. When you type everything, it will do massive of computation in the background to deduce what type and what value you are referred to. So in the last step, of course, we still need to combine this addition thing together, right? So we explicit write what we want to prove and do the proof. I won't show you here. It's very simple. And a sugar of this language is that you can use double double underline to save effort if you don't want to write so many things. If you write this underline, it will know this is the final thing you want to prove. It will deduce that if you want to close the goal, Lin will know that you are closing the goal, and it will deduce this blank for you. So you will still need the same proof, and you will see the correct thing in the info view. And when you finish the proof, you will get this example right.
In the intermediate step, can we still prove?
Yeah. You can, but it will add so much effort to Lin that he will try to figure out what you want to prove. If it failed, for example, here it's very simple. So he will know what you are going to prove. But if it fail, if in the normal case, you want to prove very long equality, right? It will figure out every item, which type it is and what value it is. So in the most case, you won't get it right. So the better practice that you just explicitly input everything. It's also more readability, because I know some of people here is doing the auto informalization, right? So if you have encountered something like this underline, if I encountered something like underline, you will not know what the underline means, because Lin do this deduction in the background. So we still, if we want to annotate the data or prove the data for the machine learning, for the LLM, so a criterion we need to follow is that we explicitly give everything here instead of let the Lin decide in the background, because it is for the readability. So since to continue that, we have already proved we have already showed that there's many structures on real number, right? So the first tactic we will introduce to save effort is ring or group. I will use ring for example, because we know a real number is a ring, so we use this ring tactic for the first time. It will use in the first place. It will use a rule-based technique to simplify the length of the equation, and try to close the goal. For example, this two is exactly same statement. And instead of do the complex calculation, we just do ring for the one time, and it's just do everything instantly. Yeah. And previously, it's a kind of tactic is not actually usable. For example, in previous improver like Coq or MetaMask, the much earlier prover, because the computer is not powerful in that period. Now the computer is powerful enough, so we can do ring, do simp, do many tactics now. So we also have a more complex proof for the inequality, which is for the multiplication and divide. This example I provide here is will contribute to our later effort to formalize our main theorem, which is the theorem I mentioned last time. Remember, we have together formalized this theorem. So today we'll try to prove this theorem. It's a very typical Gaokao problem, very typical entrance for the university level problem. It about in the last two problem in the multiple choice. Yeah. So it is at least it's not so easy for high school students. For most high school students, it's not a trivial problem. Maybe it's for us. So yes, we finished the proof, and I want to do something to explain more math behind this calculation if you are interested. I also think it's necessary because in Lin, you may also get access to, you may also met with all the difficulty of logic structure or logic derivation in the background. I will first. So the first thing is that we want to define the relations in an abstract way. If you have studied mathematical logic, you will know what I mean now. Because it's a Valentine's Day, I will denote this relation to be this simple. I'll change it today. So, for example, in type X, the X is a type. That X is a type, and this star is a relation, which means the input is either right input, left input, and you get a value. Maybe true or false, maybe another value in this type. This is what we call a relation. And we call this relation to be reflexive, which means which means the relation between for any element in this type, the relation between this is true. Any two elements has this relation. Oh, sorry, the relation we talk here it only returns true or false. Only returns true or false. So which means any member of this type and itself has relation, which means reflexive. We have seen from the previous proof, we have provided a tactic called raffle, which proves x equals x, if you have remember, right, in the last lecture. This raffle actually stands for the reflexive. So whenever you type raffle, you are proving something equals to itself. So since have this kind of relations, it has equality or if and only if, or some equivalence relation I will explain later. And the second important thing is symmetric. For example, you have x and y have this relation. You will also have, if you have x and y with this relation, you will also have y and x have the relation. It just flip around, right? This kind of relation we call symmetric. For example, in our proof, maybe we have A equals B. We want to prove B equals A, right? In this case, we use simp. We use equal.simp. I will later show you. The last and most important is transitive relation, which allow us to do many things. It's more on the structure with order. So if you have x and y have this relation, y and z have this relation, you will automatically have x and z have this relation. So how is this useful? Because we can use this transitive action to get a chain of relation, right? You have x and y and z and omega maybe, and you have x and omega have the relation. You have a chain of inequality. It's a typical use when you want to prove inequality. Of course, equality equal has its property as well. You can A equals B, B equals C, and you have A equals C. So a very famous definition in mathematics is that if you have a relation have all the three properties in this structure, and this relation is called an equivalent relation. Yeah, which means you can classify everything up to this relation. I won't explain here, but the criterion is that Coq in the back end, the Coq tactic I mentioned earlier, actually take advantage of this transitive relation. For example, if we want to prove A less or equal than Z, or A is less than Z, you have the proof of A equals than X, as A less than X, X less than Y, Y less than Z. And how can you derive the A less than Z? We use a Coq block. So Coq block in the backend actually use this transitive action to use trans to connect all the proofs you have and connect them together and get the final proof. So in the backend, it actually do this thing to prove the inequality. So why this is useful? Because for people who are now doing the formalization using LLM, maybe Coq is the one tactic, right? But if we want to generate this Coq tactic, it's usually very long. It's very, maybe about 10 or 20 lines. When you generate all this long sequence, all this long one tactic, the longer you generate, you maybe make more errors. You may make more mistakes, and Lin will fail to compile in this way. But if you know it's in the backend, it actually do this kind of stuff. You can fill the proof step by step and recursively get all this calculation right. this maybe allows the model to make less mistakes and check step by step. So this is the importance why I explain the working criterion for Coq here. So now I will going to demonstrate examples. So the first example is this tangent mode. This is simple statement which just take advantage of the previous statement I provide. So let's try to have this start working now. So I will still use the VS Code for demonstration. So what's the option for you if you cannot do the access the platform? You can type in lin live.linlog. You can type in this address. If you already installing this, you can just try in your own file. I will send this link to you for those are online. And for your offline people, you can just type this menu. For hint, I will give I will give you a theorem to prove this. This is theorem saying that tangent is equal to sine divide cosine. Yeah, you can use this. You can use this. Use this. So for those curious people, you may be curious about why we need to use these theorems like this, because in Ling, all the triangle sine cosine tangent is defined first in complex number and then mapped into real number field. So we need all these lemmas in real field to get everything right. So if you have done something, I will wait 1 more minute. Okay, I will wait no more. So I will demonstrate how to prove this in a fast way. So we prove this in 2 steps, right? We first expand because we cannot do anything with tangent. We first need to expand tangent, and then we do the calculation to get it right. So first we write the equality. This is what we expect after written out after expand tangent. So we use this theorem to we use once, and in one time it will rewrite it will expand one tangent, and the second time we do it again. It will close the goal. It will get the tangent. It will eliminate the tangent by 2 rewrite sequence. And for the second step, we can see from info view is that, which is just the lemma I provided you before, right? So we can use actually the same proof sequence. the same proof sequence in this example. This D may be changed to cosine beta, right? Yeah, and here we close the go. It's just exactly the same with the last example I provide you. In this two step, you get your first proof. And in addition to this, we still have we build on top of this, we still have things need to do before we can prove the main theorem. The first thing is that we notice in the real number field, a divided by zero equals to zero. So in the inverse way, if a divided b equals to zero, we will either have a equals zero or b equals zero by our definition. So this gives rise to an important lemma in Ling, which means if you do not have c equals zero, if you do not have c equals zero, we provide a sample that c does not equals to zero, and both a and b will not equal to zero, right? So in this case, you will never have the divide by zero behavior here. So if you do not have b equals zero and equals zero, you can actually multiply b in the right-hand side. So this is valid. This is completely valid. So how to prove this? This is a little bit hard. I will not demonstrate here. So in total, after rewrite using the criterion for a group with zero, we can see from this lemma. This actually lies in group with zero. So we're actually using lemmas in group with zero structure. So after using all this lemma, we can prove this statement. So in addition, we also have field simp. Field simp actually identify all these lemmas in the group with zero with field and automatically use all these lemmas. So we don't need to write many long proofs. We use field with simp. We use field simp, and then we can do the efficient simplification on fields. Yeah. So now it's time for us to go for our main theorem to prove the Gaokao problem. Yeah. So I will still publish this to the live. So you can copy this. You can copy this and try to prove it for some time. I will also provide you with a lemma. So for people online, you can click this link to get access to the problem. You can also copy statements in mini course. In mini course here, you can copy this statement. Okay, I will give you 3 minutes to consider this proof. Same, I will give some hint. You can say this is the ordinary equality we expect out of formalizing. So maybe I believe you have some consideration on this problem. So actually, you can identify that in this problem, the hardest part I have highlighted for you, which is this lemma. I mark it up with half block. Whenever you prove this lemma and everything in the later step will be very easy. To prove this thing, we first use the lemma we just provided to expand the tangent multiplication block. Which means we rewrite this lemma, this tangent multiplication here, and substitute it into all the sine and cosine at h2. This at h2 means you can rewrite something at a proposition, at a context variable. For if you don't know about this. And after this, you have this multiplication and divide thing here, and actually you want to move the cosine part on the right hand side. So in this way, you will need to use this very a bit hard lemma, which you have 2 does not equal to 0. No, you have this. You have this 2 does not equal to 0, which is the C we just mentioned, which does not equal to 0. And in this case, you can multiply this part on the right hand side. And for to do this, we use apply block. Because this is an implication. This is an implication. You need to input a proposition. So we apply this at h2, and we can get the right hand side right. We can successfully move the divide part in the right hand side. But in this case, we still see a gap from this part to the goal because the bracket position is not correct, right? So we use associative to get the bracket right, and we get it exact. So what's left is that when we do this apply, we can notice that there's still something we didn't prove, which is C does not equal to 0. C is 2. 2 does not equal to 0. It's a trivial thing for us, but does not for Ling. So we still need to fill this block to prove 2 does not equal to 0. It seems trivial, but since we are dealing with real number is non-computable. It's the Cauchy sequence we have mentioned before. So in Ling, the backend, you do the simp to get all this right. Of course, it's the obvious way, but if you want to know what happened in the backend, you can do simp and the question mark. And it will show you how the Ling in the backend do this stuff. So how do you do this stuff is that it have mechanism to map all the real number to the natural number. The natural number is a computable thing. We can do actual computation on the natural number, and we compare whether the underlying natural number is equal or not. And after this conversion in Ling we call type conversion. It's a very high level. It's a very hard topic in Ling. I will explain later lectures. So after this, we can get this statement right. So what's left is that we just quickly prove what's left. Because we have cosine add, cosine sub, we just replace them all. Right, cosine at h1. And we have expand everything here, and we have this. If you do not specify a name for half block, in the later part, this theorem we have proved will show pop up as a this. If you specify a name, for example, h pool, and here the name will be h cool. Yeah. So here we have the inequality for sine and cosine. So we just replace every sine multiplication with cosine. So Ling will help us simplify. So we rewrite h cool at every place. We can use this star, which means we replace this pattern at every place it found in this context, which is H2 and the goal. And so everything, so everything about sign is going to disappear. Let's see whether it get it right. I don't think it's get it right. So star is not enough. We need to write in H1, right? H1, and we wanted to rewrite in the goal we want to prove. This notation means we rewrite this pattern in the goal. And the first we rewrite this pattern in H1, then we rewrite this pattern in the goal. And then everything about sign is going to disappear. The last step is that we have this meta variable m. We don't want this m. We rewrite. We substitute this m into the goal, which is rewrite H1 is backward order. Yeah. And everything is about the cosine. We can see that this is actually a tautology. Yeah. And in this place, because we're in the real number field, we can use ring to close this. So we actually prove this Gaokao problem. We prove this problem. So what do we learn in this proof? The first thing is that it's very useful if we identify the actual difficulty in the proof and make it a half lemma, and this will simplify the proof, make the proof much simple. And another thing is that if we can first identify all the lemmas we want to use. For example, we proved these lemmas in before. We proved these lemmas before, and also we proved the division lemma before. With these two lemmas, we can get this problem right. So actually, when we are proving something, it's not as simple as proving one single problem. It's that we are providing a system. We are providing a lemma set to make the proof more easy, to make our tool, we make the tool we have more stronger. Yeah. So this is how we manage to get the proof right step by step. Yeah, and here's how we do the proof. So that's basically the course for today. Today we learn how to use calculation to prove something, and we have actually proved the Gaokao problem. So up to now we haven't get access to so many logic reasoning in Lin. So in the next lecture, we will explain more about how do you use all kinds of logic to prove things. For example, the by contrast, by contradiction, or induction, or other techniques. Yeah. So this is all for this class. Thanks for listening.